Hello, welcome to session number 7 in the series Digital Circuit Design using VHDL. My name is Anurag Nigam, and in continuation with session 6, I was talking about some of the sequential circuits, but in every session, I have to give you something new. So here I'm going to talk about various data types in VHDL. So let's put down the data types. So let me just put in a shape. Okay, so first of all, we are going to talk about various data types. Insert. Okay, and the keyword here is type. Okay, so the keyword here is type, so let's put that also there. This can be any case, so it really doesn't matter because VHDL is case insensitive. So that's the keyword which we'll use a lot. Okay, next thing is it is of four types. Okay, so it is of four types. So first one is a scalar. Okay, scalar means that it's going to take at any time only one value. It cannot take more than one value, right? So this is called a scalar. Okay, and this scalar type is again of uh, four types. Okay, so these four types are going to be an integer. So integer is one which is just a number. It doesn't have a decimal point. So that's a integer, and the keyword here is integer. And we have used this type declaration a number of times when we were doing generic. So we were using this keyword integer. Okay, so that's that. Okay, then there's another thing which is called real, and we never used it till now. So we will have some places, very few places where you'll use a real. Okay, so that would be called real. Okay, a real is something which has a decimal point. Okay, so that means that for example, a number like 1.2, 1.3, 2.2, 2.3, 2.4 or something like that, anything with a decimal. Now when you have a decimal, then there is okay, there is this concept of exponential. So you can say 1.1 e 2, so that is equivalent to 110, or you can say 100 e minus 2, that will be 1, right? So exponential is allowed, a positive as well as negative exponential is allowed, but then the number is supposed to have a decimal point. If it doesn't have a decimal point, it will be considered as integer. So that's another scalar type. The third one, which is a scalar type, which is called a enumeration. Okay, so I'm going to put that there. And what is enumeration? In other languages it is also there, right? Enumeration is a named integer. Okay, enumeration is a named integer. So I can say enumeration like color, right? I can say red, blue, green. Depending on the position, it will get some value, and that value would be an integer. So the base type is an integer for the enumeration. So if I say enumeration red, blue, green, then red is carrying a value of 0, blue as 1, and green as 2, right? So it depends on the order in which you have written the enumeration. So we will see that enumeration. Now we have used earlier different enumerations also. So for example, when I say bit, a bit is an enumeration 0 1. Then when I say std underscore logic, then it is going to be enumeration which is 0 1 z or z, x, w, uh, x, h, L and then W and then underscore. So H stands for higher priority, L stands for lower priority, W stands for weak, and underscore stands for don't care. So there are 8 values in all, okay, in std underscore logic. And if you say std underscore u logic, there is a ninth state which is called undefined or u, so which have encountered in data display window, right, when we were displaying the waveforms. We have seen u also, so that will be called enumeration. And besides enumeration, there is yet another one which will be called physical, okay. And there is, we haven't used a physical type, but we have introduced it. So for example, there is an inbuilt physical type which is time, okay. So whenever you say q is assigned something after 10 nanosecond, so we have introduced a delay concept, right, in one of the sessions, and we have seen 3 delays, right, inertial delay, transport delay, and delta delay. Now these delays are measured uh, in in form of a real, but then it has a unit, right? So any physical quantity, for example, so the inbuilt physical variable is time. That's the only inbuilt physical variable in VHDL. Other than that, it will be all user defined, right? So we will talk about physical type, and we can declare our own types. So these are built-in types. We can do a user defined types. So here I'm going to write physical, okay. For example, current, right? So I can declare a physical type called current, and then current can take units. So that's the key difference between real and physical. Physical has units, right, while real is just a number with a decimal point. Integer is without a decimal point. Enumeration is the 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 number in integer number assigned to a position in a set, right? That will be called enumeration. So these are all scalar types. Besides that, there are composite types, right? So we are going to have 2 of those. So let's put their composite types. Okay, so let me just type it. So composite types are the one which can take more than one value. Okay, and if they are the same values, that will be called same type, values of same type, they will be called arrays. So we have got arrays, and arrays can be two-dimensional arrays, one-dimensional array. One-dimensional array is also called a vector, and there is only one built-in type which we have seen, which is std underscore logic underscore vector, and it is one-dimensional. That's why it is called vector. Similarly, there is a bit vector in the library standard, right? So we haven't used bit vector, right? So it's an array of bit which can take a value from the set 0 and 1, right? So that is a array. And I wanted to tell you distinction between some things, like for example, I can write integer 1, but that integer 1 has to be differentiated from the std underscore logic, right? So that comes under enumeration. So to distinguish that, you put single quotes around this like this. So 1 here is integer, 1 in this std underscore logic is with a single quote. Also the bit is also going to have a single quote to differentiate, right? So usually in enumeration you try to put things in single quote to differentiate it from other types, right? So that's just an example you should keep in mind. And when it comes to more than one bits, then you can put in double quotes, so that will be called a string, right? So we have seen the use of a string, right? Okay, so composite type is a array, okay. Another composite type is called record, and usually unless you are doing testing, if you are doing synthesis, you will not see a record. There is no way record can be synthesized. Okay, so record means that this is going to be a collection of or a list of different types, right? So I can put in an integer, one type, one variable or two variables or more variables with integer types. Then we have got real types, and we can mix them in a record. So but a record, okay, is a composite type where it's a collection of different types, while array is a collection of same type, right? So that would be called a record. So now let's see the fourth data type, which is called the access type. And the access type is like a pointer, okay, like a pointer in C, for example. So we have got access type. Okay, and access type is not synthesizable, and though it can be used in some form of a function, okay, and but it will not be synthesizable, right? So access type, and it might be used in some form of a testing or verification, right? But rarely you will find a use of access type. Then there is something called file type. Okay, so there are file objects. So basically, let's say test vector, okay, and you want to put a text vector in a file so that when you turn off the system or FPGA, okay, so that test vector is gone. It's in the volatile memory, for example, the memory which you use. So now you can put it on a flash card, for example, right? So if you put it in a flash card, you can put it in a file, right? So then there is a another type which is file. Okay, so these are the four basic types, and then there are subtypes here, right? Okay, so the keyword here is type. Now why I'm putting here a keyword type, because there are inbuilt types and then you can create your own types. Okay, and this is many times done for improving the readability, right? So we will come to all this somewhere, right? So I'm not going to use them directly, but I'm going to do custom types. Now the question comes is, once you know the type, then where are you going to declare it? For example, if you go and declare it in a package, okay, if you do go and declare in a package, so whichever entity you are going to refer to that package, that entity would have access to those types, right? So this is called global type. Okay, so it is seen by it can be seen by any entity which you write, as long as it references to that package. So that's a global type. Then you can put it inside, let's say pick up a circuit, let's say T flip-flop, right? So let's see the code for a T flip-flop. Now I wanted to tell you this, okay, this is the entity, right? Now this entity, this region is known as the declaration section of an entity. Entity can also have a begin, and this is perfectly legal, right? This is perfectly legal. It is not going to complain you. Now the entity has got two parts. One is the part which is the declaration section, and the other is the body. Okay, so you have a body, and in the body you cannot do any assignments. You can only do assertion. Okay, and I'll tell you what is assertion. Assertion means that if some condition is true, okay, or if some condition is false. So if a statement is like, if some condition is true, then do some statements. But in assert, if a condition is false, then do something. And that doing something can be report an error, report a warning. Okay, so report, okay, is another keyword here. So you say assert condition report, right? And then after that you can say severity of that report. Okay, so So when you say you report a message, so you pass on a string, and then when you say severity, it can be a warning, it can be an error. Error means that the VHDL code is not going to execute as soon as it encounters a error. It cannot be compiled even. While while when you have a warning, then the compilation still goes through. Okay, so when you do assertion based testing, you can have assert statements here. So what I'm telling you is entity is basically has both declarative section as can have an optional body also. Okay, so in this declarative section I can define my type over here. So if I do this in entity, then all the architectures of that entity can see it. Okay, so that is the scope of type declaration here. Now you can declare a type in the declarative section of architecture also, or in the declarative section of process also, or in the declarative section of subprograms called functions and procedures, which we haven't covered, but in their declarative sections also you can do. So wherever they are, the lower level to that, okay, would have the scope. So that you have to keep in mind, and you can go from a global in a package to a entity wide in an entity, and to architecture wide in architecture, to a function wide in a function or a procedure, to a process wide in the process statement, right? So all this can be done. So we have got variables, right? So these types are nothing but you can declare some variables of a certain data type, right? And the declaration can be a signal or a variable. So you should understand the difference between a signal and a variable. I think I have told you earlier also. Let's see if I mention this. Okay, signals are like wires and they have drivers, right? And they can have multiple drivers. In that case, you have to have a resolution function. Okay, signals have attached properties that are called attributes. So for example, clock, tick, event. So usually you write an attribute as a signal with a tick and then event. Okay, some people confuse. Okay, while in Verilog you might get confused between a single quote and a tick. A tick is somewhere which is going to be uh, the same key button as tilde in the left top corner just below escape, most probably in most keyboards. Okay, while apostrophe is basically a single quote, right? In VHDL this single quote works, but in Verilog you have to use a tick. You might spend a lot of time why the code is giving you a problem because you haven't used a tick, right? So these things you have to keep in mind, right? And yeah, so the properties are basically the attributes are nothing but the properties which are attached to a signal with a tick sign, right? So for example, event. So event is attached to a signal. An event means that there is going to be a change in value that is considered as event. But if you evaluate an expression and you assign it but the value didn't change, okay, if the value of the signal didn't change but then the expression involving the signals on the right hand side of the driver, right, or assigned statement, okay, if that expression is evaluated but then there is no change in the value, so that is called a transaction, right? So events means the change in value, transaction means no change in value but the expression is evaluated, right? So that's there. So just like event, there is another attribute called transaction. Okay, so fine. So we know signals have attributes, while variables are memory locations. Okay, they do not have properties. They are stored in a memory location, and signals are basically wires. They are driven. So if they are driven by a driver, then there are delays of assignment, right? So if you say Q is assigned AX or B, A and B are in the sensitivity list which undergo AND operation, A and B. So this expression is evaluated. But if the Q value is the same as the previous value, then we say transaction has taken place. But if the Q value has changed when A and B is evaluated, then it is called an event, right? So that part is clear. Now, the assignment doesn't take place immediately, as we have seen in case of delays. Okay, it is a delta delay, right? Or it is a inertial delay, or it is a transport delay. While in case of variables, the assignment is immediate because it's just stored in a memory location, right? So signals take more space, okay, while variables take less space. So variables are more efficient than signals. Okay, another thing is that the signals can be declared in the package. In the declarative section, you'll say package, right? It can be declared in the entity. It can be declared in the declarative section of the architecture, but they cannot be declared in the declarative section of a process or a function or a procedure. So this you have to keep in mind. While variables can be assigned only in the declarative section of procedures, functions, and process block. Okay, so variables their uh, find their value or find their use only in case of sequential statements, and these sequential statements are found inside process block, functions, and procedures. So that's where the variables are used. Now besides that, there is something called constant. So if you use this keyword constant, then you can say constant, and by the way, it doesn't matter if it is capital C or small c, and then say constant A is of type std. I'm just telling you what these constants are. Logic. And then I can give it a value. Okay, for example, this default value is 1. Okay, so this is a constant declaration. Now A cannot change its value. Okay, if you try to assign to A, it will come up with a warning. So for example, in design, you can have a constant VCC. Now VCC is assigned 3.3 volts, for example. Now it cannot change its value, right? So how would I define that? I can say constant, okay, and then I can say VCC is in this case, let's say real, okay, and it has a default value of uh, let's say 3.3 volts. Okay, so this constant cannot change value. Now the constants can be, or uh, any variable can be declared locally in the local scope. In that case, that takes a priority over the global scope in that block, right? So you can have this constant specify at the global level when it is done in a package, right? So all circuits are going to work on 3.3 volt, for example. So you do it in a package. If you do it for an entity, that means that only that component is going to work at that voltage, right? So what I'm saying is constants also have the same scope rules, right? And the constants declared in the declarative sections. Okay, so a package, entity declarative section, or a architecture declarative section, or a process or a function or a procedure declarative section, right? A constant, okay, a constant should always carry a value, okay, if it is not given in the declarative section. If it is something like just like that, then it has to be given a value in the package body. So if you introduce a deferred constant, right, in a so that is called a deferred constant. A constant is declared, but it is not given a value. It will be given a value in the body of the package, right? So package has a package body. So we'll see this later on when we deal with subprograms. Similarly, if you do this in the declarative section of the entity, you have to put in begin, and then you would have to do a default value of a constant. Okay, so deferred constant have to be immediately addressed in the body of any entity, right? So so that being clear, deferred constants are not going to be so commonly used. Okay, and as such, even constants are not so commonly used initially, right? So we are not going to talk a lot about that. Okay, so now we know various data types and we know various constants. So let's see some examples. Okay, so let's make a design source. Okay, and say create source, add source, and say next. And here, let's say create file, and here I am going to create a file named exercise type. So I'm going to show you various type declarations here, and then the library is my circuits. I could have shown you, probably not in this, maybe in package itself, right? So the scope is global, so let's go here. I don't want to create a new uh, RTL design unless I need it. So this is a good place to declare constants. You can declare them anywhere. Okay, so this is the declaration section, declarative section of a package. Okay, so I can put here type, let's say color is, and then I can put the round brackets. I can put here red, blue, and green. Okay, and that's it. So okay, so this is declared over here as red. Okay, let's save it. Okay, so let's open any file. Of course, I am not going to change it. I'm going to undo the changes. Okay, so now let's say the one which refers to the package. So for example, here it refers to a package, right? So here, this is just an example. This has nothing to do with D flip-flop. So I can write here case. Okay, so I can put here a type, right? So I can declare a signal. So I can say signal, my color, okay, is of type color. Okay, so notice that it knows what is a color, right? Okay, and then here I can say color is assigned red, right? So it is a signal. Color is not a signal. Oh, it is a type, sorry. Mistake, my mistake. So my color is a signal which is given a value of red. Now, mind you that red has to be there in the set. If red is not there in the set, it will not take a value of 0, right? So here the red is the first one, 0, blue is 1, green is 2, right? And I'm showing you a case statement, right? So I'm going to show you a case statement. So this is a sequential statement, so you cannot write it in the body of an architecture. You have to use a process block. And I can say process, and I can say this is affected by my color. So that's the sensitivity list. And I can say begin, and then I can say end process. Okay, so if I want to put sequential statements, they have to be inside a process block, right? Then I can say case, okay, my color is, okay, and then I can say when, and when it takes a value of red, for example, okay, when red, then you have a sequence of statements. Okay, so what you can do is you can say D is assigned 1, for example. So this is nothing to with the D do with the D flip flop, but I'm just showing you how to write the how to use that enumeration, and then it has to have end case. Okay, so you don't see, okay, you see red lines. Syntax error near this. Oh, case begin. Okay, wait, case doesn't have, so I'm a little confused. Let me put you on a hold because I do other languages, so I get confused. Okay, sorry for this mess up. Okay, into different languages, so I get confused. Okay, so this one doesn't go like this. Okay, when red, do something, and that's how you do it. Okay, when red, do something, then you can say when blue, do something, when blue, do something, right? And when, I'm not sure if there's a default in this case. I think when others will also work here, or it doesn't need that. When others, do something. Let's see if it accepts that. Okay, so let's see if it comes up with a red line. It doesn't, so it does accept. So after I have exploited all the choices of my color can be red, I'm doing this. When it is blue, I'm doing this. When it is others, I'm doing this. And end case. So I can use, with the case statement, I can use an integer here. And I can also use an enumeration, because enumeration internally is an integer only, right? It is the position number, right? So that's how you use an enumeration, right? So I hope you understood what is enumeration. So I'm going to just delete this because that's not what a D flip-flop does, right? So what D flip-flop does is only up to here. And I'm going to remove this because, again, okay, so it is a type declaration, so it can be true for signals as well as variables, right? And their scope rules are valid. Okay, so let's go to another type declaration here. So this is a enumeration. Then I can say type, for example, let's say I want to show you physical, right? Okay, I have already shown you integer, right? So I have said in case of uh, integer, it is a, you don't have to declare it, but you can do a sub, uh, you can say do a subtype. Okay, so can I do a subtype is integer range 0 to 10. Okay, so okay, I haven't given a name. Okay, my int. Okay, subtype my int is an integer range 0 to 10. Now my int is an integer, base type is integer, but then I have fixed a range from 0 to 10. So my int cannot take any values other than 0 to 10. So this is a subtype declaration, right? Similarly, for real, I can do a subtype. Okay, so let's see if it works for a real. I have never done it. Subtype my real is real range 1.0 to 3.0. Let's see if this is going to work. So it did, it didn't. Yes, it did. So basically with integer and real, you cannot declare user defined types. You can only do a subtype of that, right? So with enumeration, you can declare your own type. Okay. Similarly, for physical, you can declare your own type. For example, you can say type current. Okay. Type current in. Do you have to put in? In is a keyword, right? In range 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I can say units and end units. Let's see if this is correct. Okay, so you can, so there is no in keyword used here. Okay, so now what is the problem? Okay, so now I can start. So notice that this range, okay, is going to the power 9, right? So if I start with nanoamperes, for example, so that will be the base unit, right? Let me just see why there is a red line, right? Sometimes I have to revise this stuff, right? So let's see why there would be in the physical type declaration. What wrong am I doing? Okay, just give me a minute. Okay, enumeration, physical types. Okay, so I have to put a is keyword. Okay, okay, so type current is range 0 to this. So the base type here is still an integer, right? Okay, and then I can say the base unit is nanoamperes. Then I can say what is above nano? It is picoamperes. Picoamperes is equal to 1000 nanoamperes. And then I can say microamperes is equal to 1000 picoamperes. And then I can say milliamperes is equal to 1000 microamperes. Now what's the problem? Okay, so now I have exploited the entire range of 10 raised to 9. Okay, that uh, is restricting. Now I can I do this? I don't know if there is something called implementation defined. Okay, let me see if I can do that kind of stuff. So it's always good to keep, Douglas Perry kind of a book handy, right? So implementation defined is going to be 2 words. So does it work? Now does it allow me type this range implementation defined? Implementation defined. There is nothing called implementation defined. Implementation oh, spelling mistake. Okay, so implementation defined. I don't know why it should give you error. Type current is range, implementation defined units, end of units. Okay, doesn't allow you that. Okay, so that doesn't seem to work. Okay, okay, maybe I'll address this later on. But here I have a range 0 to 10 raised to 9. If I exploit that, I cannot go further. 0 to 10 raised to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's see if I can put in more 0. It doesn't allow me, right? It can only allow me 9 zeros. Okay, so I have declared a physical type here, current, which is and a base type is an integer, and the syntax is type, name of the type is range 0 to this last value units, and then the base unit is nanoamperes. That means that I can go 10 raised to 9 nanoamperes. That will be milliamperes, right? So that's how you do it. Okay, so that's how you do physical type, okay, of your own. Now let's see arrays. Okay, so I can do type my byte is array, type my byte is array 0 to 7 of std underscore logic. Is that a valid statement? Yeah, so that turns out to be a valid statement. So type my byte is an array 0 to 7 of std logic. So here the index 0 is the MSB and 7 is the LSB. So if I have another declaration, if I say type your byte is array 0 to or 7 down to 0, 7 down to 0 of std underscore logic. Okay, so the base type is here std underscore logic. Okay, so now if I take instance of my byte and assign it to instance of your byte, the bits sequence is going to reverse. Why? Because here MSB is 0, LSB is 7, and here uh, MSB is index 7 and LSB is index 0. So it will go MSB to MSB assignment, LSB to LSB assignment. So it is going to reverse the word. So some number of places when you have to flip the signal, you can do something like that, but I won't recommend that. Okay, because it doesn't have the readability of the code, right? So this is how you declare the array, right? Now I can also say type memory is array, let's say 0 to 15. So this is 16-bit wide, or rather there are 16 location of std underscore logic underscore vector, right? And here I can put here 7 down to 0. Okay, so now here is a declaration of memory, which is an array of arrays, right? So vector is itself an array, and this is a 16 locations. So these are 16 rows of that memory. Okay, 0 to 15, and then the columns are 7 down to 0, right? So MSB is 7, LSB is 0. So this is how you do a two-dimensional array. Now You can also do the same thing using this way. My memory is array 0 to 15, okay, comma 7 down to 0 of std underscore logic. So this is a two-dimensional array. Let's see if this is correct. Yeah, it is. Okay, so you see I can define it in two ways. Internally they are going to be the same, right? Now up to this point everything is okay. So now let's say if I have to assign my byte in my program or a code. Okay, so let's go to this one itself and say I have a signal, and that signal is going to be received byte, rec byte, okay, and it is of type memory, or it is of type my bytes. For example, let's do with a single dimensional array my byte, and then I can give it a value, right? So I can say my byte, okay, and if I want I can give it a default value, and I can give the default value as 0 comma 1. So now this is a std logic vector, so I have to put quotes around it. 0 comma 1 comma 0 comma, so comma 1, and let's just repeat it because this is 8-bit wide, so I have to provide 8 bits. Okay, so what did I do? I declared receive byte as my byte, which is a user defined type, and given it a default value. So this is how the array is declared. Now if I want to access a member, then I should be able to do receive. So if I say if, then a condition receive byte, and then a location, let's say 7, okay, equal to 1. Okay, so let me put this inside this. Then I'm going to do something and say D is assigned 1, and it should be and if. Am I correct? So let's see. If, is there a then statement? So I haven't done statements yet. So it doesn't work. If and then. Okay. Okay. Most probably. Sorry about that. Okay. Let's refer to Douglas Perry again, because I haven't covered anything on if statements, but I'm using it, right? If then is a keyword, okay, and if is also a keyword, so everything looks okay to me. If then is a keyword, then, so what has gone wrong here? If capital or small doesn't make a difference. Capital or small doesn't make a difference in VHDL, but you still do it. So why is it red colored? Syntax is wrong. Oh, again the problem is this is a this is in the body of a architecture, so you cannot put that directly there. You have to put it in a process, and you can process you can put this empty, for example. Let's say if this works, then you can say begin, and I'll discuss processes later on, and say end process. Okay, warning syntax. Okay, t equal to 1. So this is all fictitious, but if so, this is sensitivity list t. Okay, fine. So I just put the statement in a process block. Okay, so if then I access the 7th bit and I'm checking if it is 1, then d is assigned 1. So I'm just demonstrating how you assign values to an array and how you access a particular bit. So that's all I'm trying to show you. Okay, so if you go here, this is the declaration, and this one or sorry, this one or this one, this is going to be the same way. Now type memory, right? So let's do a two-dimensional array. Okay, so if I want to do a two-dimensional array, so right now this is big, right? So I don't want to do that. So let's say had it been only two values. So just to simplify this, okay, just two values, then I could have said mem, okay, is assigned. Now the dimensions don't match, so it is giving you a warning. So I can put here another one, I can put here a comma, and then I can put here, I'll just repeat the word, which is this. I can put it here and then closing bracket. So what's the problem now? Just wait. Okay, composite types. Did I forget something? Rec byte is a memory with a default value of this. Syntax error near this. So what should be the syntax error? So let me put you on hold. I figured this out. Okay, I was putting a brace here. I'm used to other languages, so that's why it was giving me a problem. Okay, so now you immediately see that I have declared a 2 bytes as 2 locations in the memory. The word size is 7 down to 0, and it immediately starts complaining. So I want to look at the first byte and the 7th bit. That's okay, is it? Index name prefix type mem expects, hang on a second, expects 1 dimensions. Okay, now there's a difference in the declaration, so I have to do like that. Okay, so if you define it this way, then you have to put 2 brackets for 2 dimensions, and then you can compare it. So that's how you will do a 2-dimensional array. Now let's say if this was my mem, which is defined slightly differently. Okay, again the filling up was correct, but now there is a problem here, and in this case it can be comma separated. Okay, so it depends on how you declare the two-dimensional array. Okay, your indexing would be either first index comma the second index, in case it is going to be declared like this, and if it is declared like this, then you would have to do an indexing which is going to be first bracket first index, second bracket second index. Okay, so I hope I explained you how do you do arrays here, right? Then there are some more types, like for example you can do a record, right? So let's say, so records are, you know, slightly different from arrays. Arrays have only one base type. Records can have multiple base types. So I can say type, and I can say here okay, my book is, and then you say record, and you can say end record, and inside this, so let's see again. Okay, so I have to declare something inside this. Then I can say here okay, my color is of type color. So now what's the problem? Oh, there's a colon, semicolon missing. Okay, so I can put here that, then I can say my info is of type my byte. Okay, so this is how you do a record. Okay, then there are access type where basically you can do it this way. Let's say for this one access type, right? So I can do here type my point. So that reminds me, it's a pointer, is access type my byte. Is that correct? Okay, just one second. Just one second. Okay, is keyword. Type, name of the pointer is access type, right? Access type of my byte, and this. Okay, so now I have a pointer, my point, which is pointing to which is a pointer to my byte type. Okay, and then the way to dereference it, okay, the way to dereference this would be, let's go here, let's say that this was my byte. Okay, and that means that there is going to be only one word, so the width is basically just that, right? So this is my byte. Okay, and here I am not using a if statement, so let's get rid of that. This is an empty process here, and I'm not using if statement, so I don't even need a process. So I can say, okay, w is assigned, okay, and after that I can say rec byte, rec byte, rec byte. Okay, so now I have created here a access type, which is my point, and is a access type to my byte. Okay, so the types are declared here. So here I have this my byte declare here, right? Now let's say, so I should have said that, okay, fine. Okay, that's correct. Maybe I can declare it somewhere else also. Control X, right? And then I could do an assignment here. In this case, let's say I have another signal defined, which is a pointer, right? So our pointer is called my point, right? Okay, pointer of type my point. It has to be given a default value, which is null. Okay, then I can, instead of addressing it with rect byte, file type, right? Uh, oh, oh, the pointer will not be done like a signal declaration. So wait here. I can say pointer equal to new. So there is some form of a constructor here. New, and this type is called my point, right? My point, is that way? Hmm? Okay, so we have to keep in mind that access type access is a pointer, and pointer is basically a memory location. That means that it cannot be mixed with signals. So having said that, you see here I have declared type my point. My point is a new type declaration. Is a access, means it's a pointer to my byte. So my byte is going to be a 0 to 7, right? So now if I was to use this pointer, so how would I use that? So let's go here to demonstrate this. So let's say that I have a signal which is my byte and rect byte. Okay, so I have a signal, so this is not required. Okay, so I want to access something through a pointer, right? So it has to be treated like a variable. So I can say variable, and I can say here pointer is of type my point. So this is a this thing and has a default value of null, correct? So now the pointer is defined. Now I have to point it to somewhere. It is pointing to null right now. So I can say pointer, okay, is going to be given a value which is going to be a constructor, and then it is of type my byte. So it's pointing to that. So I have created here a new object, okay, my byte, okay. And if I had done it over here, I could have just assigned it, right? So then, so I have created an object without, you know, without giving it a name, right? I have created an object of type which is an array without creating a name, but then I have assigned it to a pointer. So now I can assign the values to a pointer by using dot all is assigned, and then I can declare my byte here as 0 comma 1 comma 1 comma 0 or 1 comma 0, and so I have to put eight of them, comma 1, comma 1, comma 0. Let's see if there are 8 of them. So I have got 1, 2, 3, 4, 5, 6, 7, 8. So now I have a pointer rather than name for that array. So array basically is a pointer. So now I'm using it with a pointer. So I have assigned this memory location dot all with this value. Now if I want to access this, I would say if, let's say I want to compare the 7th bit, so I can say pointer dot all, and then I can index it out. Index 7 is whether it is 1. Okay, then do something which is d is assigned, let's say 1. Okay, and if so now this is all legal. Okay, so what did I do? I created my own type, which was my byte. Okay, and then I have created a pointer to that array. Okay, so this type is going to store pointer to only this kind of arrays, right? So initially I went in here and I created a variable which will store a pointer to that array, and the base type of that array is going to be what is pointed by my pointer. Okay, my point is the base type for that array. Okay, so that's a pointer. So I have declared a pointer variable and given it an initial pointing location to null. Then here I generated a new array. Okay, and the pointer which is returned by this new constructor is assigned to this variable pointer, and then pointer dot all, okay, is assigned a byte, and then from that byte I have indexed 7th bit, or 0 to 7. So basically LSB here is 0. If it is equal to 1, then do this and if. So you can see how I have used the access type. So this basically completes various types other than the file type, right? So file type I'm not going to cover here. Maybe when we do test vectors and you want to write it to a file or read from a file, at that time I would show you how to do this type. But we have covered all the data types which are there in VHDL. So I'm going to end the session here and see you in the next session. Thanks a lot.